All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing tonight? Good, good. All right. All right, so the plan for today is we're going to move on to the next topic now. So we just finished our introduction to the direct stiffness method. And so next we're going to start incorporating different element types into our analysis. So the first type of element that we're going to learn about is called a truss element. Okay. You'll see that it's very similar to a spring in terms of how we use it. It's just that you plug in different properties. The biggest difference that we're going to see in this unit is that we're going to move on to 2D analysis, right? So we're going to do some 2D truss problems, and we're going to see kind of how to solve those. Okay. All right, but the first thing I want to do today, just because last time we didn't get a chance to do it, is we're going to learn how to solve linear systems in MATLAB, so you can do the homework and stuff. Okay. Speaking of homework, I think most people in the class have already done it, but if you haven't sent me your introduction email, please make sure to do that. The due date for that is tomorrow, so please make sure you just shoot me an email real quick. Just say your name, I'll respond to you, and then if we can get that, I can get you credit for that. And then the first problem set was posted just yesterday as well. Okay, so there are 6 problems on it. So there are 6 problems in direct stiffness method, 3 1D problems and 3 2D problems. Right now, I've set the due date for next Sunday to be for now, but we'll see how far we get today. And so if we don't get as far today as I originally planned, I'll probably push that back a few days just to give you guys some extra time. Okay. Because the problems are fairly lengthy, especially the 2D problems. So you definitely want to start early, and I want to give you guys enough time to do. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go get started. And so the topic for today is truss elements. Okay. So like I mentioned, we've seen the entire direct stiffness method at this point, right? And so it's the whole process of writing the element stiffness matrices, assembling your global system, applying boundary conditions, and solve. Oh my God, wait, I'm getting ahead of myself. Let's do the MATLAB stuff first. I'm sorry about that, guys. I mentioned it and I forgot about it literally 1 minute later. Okay. So speaking of the direct stiffness method, at the very last step of direct stiffness, what you need to do is you need to solve a matrix set of equations like this. Okay. So I'm just scrolling up here. So this is the example that we ended with last time. And so I'm going to show you how to solve this system here in MATLAB. Okay. So here we have a 4x4 system. We have 4 equations and 4 unknowns. Our matrix here is 4x4, and our forcing vector here is 4x1. Okay. So to solve the system in MATLAB, basically what you need to do is you need to input this into each of these into a data container within MATLAB. Okay. So we're going to have one variable that stores the matrix. Okay? And we're going to have another vector or another variable that stores this thing here. All right, so let's start with that. So let's open up with MATLAB, and I'll show you how to create variables and create matrices and vectors. Okay. So let me go ahead and share my screen. Okay. So I'm just going to go fairly quickly here. If you happen to be on a computer with MATLAB, you can follow along. If not, this will be in the recording as well. I can post a script onto Canvas as well, but it's going to be fairly simple. Okay. And so if you've never used MATLAB before, when you first open up MATLAB, you have a window that looks like this. Okay. What you have first here is you have what's called the command window. And so you can actually, put things into the command window, and it's basically going to be just like a calculator for you. So if you do 2 plus 3, it's going to give you the answer of 5. Okay. So you can actually do all this through the command window as well. But what I always recommend for people is that if you're kind of new to MATLAB or you're just learning MATLAB, do everything in a script That way you can save the script and kind of read it later, and it's kind of easier to kind of debug issues from the script. Okay. All right. So to create a new script, you're going to go up to the top left corner here. So you're going to click on new script. Okay. And this is going to open up a new, basically a new word processor here for you to start writing MATLAB code. Okay. Okay. So the amount of code that we're going to write here is fairly simple. So remember, like I just mentioned, you need to have one variable that stores the matrix and another variable that stores the vector. Okay. So I'm going to write some comments here just so that you can kind of see what I'm doing, but the comments are optional. And so if you've never done MATLAB before, if you start a line with a percent sign, this is something that's called a comment. And so a comment line is only just for humans to read. The computer doesn't read the comments. In fact, it just kind of skips over it. Okay. Okay. And so this is basically just for our information here, just so we can kind of stay organized. Okay, so we're going to create a variable to hold the coefficient matrix. Okay. All right. So to create a variable, you basically need two things. And so you need to have a name for the variable. And so for this variable here, I'm calling it A. Okay. And you need an equal sign. Okay. So the equal sign is basically called what's called an assignment operator. So the equal sign will basically say that whatever I put on this other side here, I'm going to store that within that variable. And then that variable is something that we can access and use later on. Okay. So let me show you how to make a matrix. Okay. And so to make a matrix, you're going to create this matrix row by row. And what that means is that we're going to input the rows of the matrix starting from the top and going down. Okay, so let's do the first row in the matrix. And so for this particular problem, our first row is 1, comma 0, comma 0, comma 0. Okay. So remember that row there corresponds to the Dirichlet boundary conditions. Okay. To go to the next row, what you need to do is you need to add a semicolon. Okay. And then one thing that I like to do, this is optional, you can do it all in one line, is you can add 3 periods here, okay? Just so that you can kind of go to the next line, just so you can kind of visually, it kind of looks like a matrix, okay? All right, so the next thing we're going to do is we're going to input the next row. So we're going to do minus 500, 850. Remember, we're separating everything with a comma, okay? Minus 100 and minus 250. Once again, we're going to have a semicolon, okay? Dot, dot, dot. So semicolon, dot, dot, dot needs to go to the next line. Okay? Then we're going to import the next row in the matrix. We have 0, comma, minus 100, comma 100, comma 0. Okay, semicolon, dot, dot, dot. Okay. And then we're going to enter our final row in the matrix, which is 0, comma minus 250, comma 0, comma 250. Okay, so that is our matrix. And so you can see we've built it up row by row, starting from the top. Okay, our first row is 1, comma 0, comma 0, comma 0. We add a semicolon. The ellipsis, the dot, dot, dot is optional, but I like it just so you can go to the next line. Okay, then we built it up kind of row by row from there. Notice how we encapsulated everything in square brackets. Okay, so the square brackets tells MATLAB that this is all one data container. Okay. And then we have a semicolon at the end right here just to tell MATLAB that we're done with this line. Okay, so let me go ahead and save this. We'll call this mat solve example. All right, and so to run your code, you can either, what I like to do, I like to hit F5 on the keyboard, or you can just hit the run button up here. Okay. Okay, and so now that's created our matrix. Any questions on this? Okay. Okay, so now that we've created our matrix, we now need to create our forcing vector. We're going to create a variable to hold our forcing vector. Okay. Okay. All right, so just like we did with the matrix, we're going to create a variable for this. And so our variable for this one, I like to use the lowercase b. Okay. It's very traditional for linear algebra. Once again, I'm going to use the square brackets, okay, to let MATLAB know that I'm creating a data container. And just like with the matrix, we're going to build this up row by row, and we're going to separate each row by semicolons, okay? And so if you look back in your notes, our forcing vector is 0, semicolon 0, semicolon 100, semicolon minus 50, okay? You can see here that I didn't use the dot, dot, dot just because this is just a column vector. So each row only has one entry. And so just to save a little bit of space, I put it all on one line, okay? All right, so now that we've created these variables, we're now ready to solve. And so to solve a linear system, we're going to use the special backslash operator. Okay. Right. And so if you're wondering where the backslash button is, it's the button that's right above the enter sign. So usually we use the forward slash button. The forward slash looks like this, right? So you're entering a URL or something like that, use the forward slash. But to solve a linear system, MATLAB uses this backslash operator. Okay. Okay, so to solve the linear system, all you have to do is you have to do just A backslash B, okay? So you have your matrix variable A, you have your forcing vector B, and you just separate them with the semicolon, okay? All right, so I'm going to run this code. Notice how I didn't put a semicolon here, and so I didn't put a semicolon just so we could print our results, okay? And you can see here that this is our answer right here. So our answer here is 0, 0.1, 1.1, and minus 0.1, okay? For this top one here, this is our D1, this is D2, D3, and D4, okay? All right, and so that's kind of a crash course in how to solve these things in MATLAB. So you know, I know I kind of went through that pretty quick, but basically all you have to do is just define your variables here. So define a matrix, define a vector, and then just use the backslash operator. So you know, if you didn't put the second lines, if you didn't put the comments, it's literally just 3 lines of code. And so you know, you can use this to solve the linear systems in the homework, or kind of anything that we do in this class. Okay. All right. Any questions on how we did that? Okay. All right. And so that's you know, for everything in this class, you know, we're always going to get to the point where we are going to solve the system, but we never solve the system by hand. So I always let you kind of use a computer or a calculator or whatever to solve these systems. Okay. And same thing goes for the exams too. And so, you know, these kinds of problems, these direct stiffness problems, are going to show up on the exams. You know, but I'm not going to make you actually solve this system. So that's, to me, that's just kind of a waste of exam time. So I would want you basically to set up a system like this, set up the matrices, and then that's what I would grade you with, basically. But for the homeworks and for the projects, you do have to solve the system, and that's how you would do it in that way. Okay. Okay. All right. So let's go ahead and move on. So our next topic here are truss elements. All right, so truss elements, you know, this is going to be kind of building off what we've done before. So we've learned about the direct stiffness method, but we've only used springs. Okay, and so a truss element is a different kind of structural element that we can use with the direct stiffness method. Okay, so the process that we're going to follow to solve these problems is the same. The only difference here is that, you know, because the truss element is a different kind of element, it's going to have a different element stiffness matrix. Okay? That's the only difference. Okay. We're going to follow the exact same process all throughout. But what you'll see is that a truss actually behaves very similarly to a spring, in the fact that for a truss element is a slender, usually a slender structural element that's only capable of tension and compression. Okay. And so visually, we usually use like some kind of a thin tube to represent a truss. Okay. And the only deformation modes and the only kind of forces that it can support are forces and displacements in the axial direction. So that's either tension or compression. Okay. All right. And so let's look at the element stiffness matrix first for a truss. Okay. All right. So recall, our element stiffness matrix, its main role is to relate um, external forces or external effects on our element and the corresponding response or corresponding deformation. Okay. All right. So let me go ahead and draw the truss element again. Okay. And just like we did for a spring, we're going to assume we have a static equilibrium. Okay. And so what that means is that we're going to apply an equal and opposite tensile force on both sides. Okay. This is static equilibrium. Okay. We're going to call the left node, we'll call that node 1. The right node we're going to call node 2. Okay. Let's define a few more properties of this truss bar. So let's assume that we know the length. Okay. So the total length of the truss bar is given by L. We know the cross-sectional area. Okay. So I've drawn a truss bar here with a circular cross section, but that doesn't necessarily have to be the case. You can have square cross sections, rectangular cross sections. As long as you're able to compute the cross sectional area, you know, anything is fine. Okay, so we'll define the cross sectional area as A. Okay. And we'll say that we know a little bit about the material that's being used too. So the material has its own Young's modulus or elastic modulus. Okay. And we'll give that the symbol capital E. Okay. So that's our standard kind of truss element in all of the relevant properties. Okay. So let's put some math on this. So let's form our equations here. So let's assume we're going to make the assumption that we have linear elasticity. So our stress-strain relationship is going to be linear. Okay. And so what that looks like is we have this formula here, which is Hooke's law in another form. Okay. That should give you a hint about kind of where we're going with this. Okay. And so Hooke's law for a general kind of elastic material is we have sigma here. So sigma here is our stress. Okay. E, of course, this is our Young's modulus, or elastic modulus, whatever you learned it as. Okay. And then epsilon here is our strain. Okay. So what we're going to do here is we're going to plug in for the stress and the strain here and relate it to the properties and the geometry of the truss bar that we have. Okay, so let's start with the stress. And so stress is nothing more than a force distributed over an area. Okay? Stress has the same units of pressure, so it's force over area. Okay, SI unit for that is pascals, and then the English unit mostly is PSI, pounds per square inch. Okay. Okay. So let's see if we can relate that to some quantities that we have here in our truss diagram. Okay. So we have a force. We're applying a tensile force of T on both sides. Okay. And we have the cross-sectional area, right? And so the stress is going to be nothing more than that externally applied force distributed over that area. And so what we can do is we can say sigma is equal to T divided by A. Okay. All right, let's look at the strain. So the strain here in a one-dimensional case, we can define the strain to be a relative change in length of the truss bar. Okay. Because what we expect is that if we have our structural member here and we're applying a tensile force, we're pulling it apart, or even a compressive force, we could be trying to push it in, right? Our intuition is telling us that the bar is going to deform or it's going to change in length in response to the loading, okay? And so that strain there is the relative change in length, which is basically the change in length divided by the original length, okay? And so what we can say is that epsilon here is equal to, let's call it D2 and D1, okay? All divided by L. Remember D2 is the deformation of node 2. And D1 is the deformation of node 1. I'm only labeling that there because I forgot to label it in the figure as well. Okay. But D2, D1, those are kind of the familiar quantities that we saw from the spring. Okay. All right. So we're going to plug in these quantities in for sigma and epsilon, and that's going to put our expression here in terms of first of all, it's going to put us in terms of the material and geometric quantities of the truss bar, and we've gone ahead and factored in our nodal deformation, and so we're kind of setting ourselves up to create our nodal, or excuse me, our element stiffness matrix. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and plug these in. So sigma, we're going to have T over A. Our Young's modulus, we're just going to leave it alone. That's just going to be E. And then we have D2 minus D1, all divided by L. Okay. I'm going to multiply both sides by A. And I'm going to pull out the L from the parentheses. So we have T is equal to E times A over L times D2 minus D1. Okay. Okay. So this is good. So what we have here, so let me kind of pause here for a second. Let me underline this. Okay. So what we have here is a relationship between the externally applied force T and the nodal deformations of the truss bar. Okay. Let's use this expression to relate it to kind of forces in general on the truss bar. Okay. So we're using basically the exact same approach that we took with the spring. Okay. Actually, let me redraw the truss bar here, just because I was kind of missing some labels above. Okay. So we know that the left-hand side node is node 1, the right-hand side node is node 2. Okay. And so we know that the deformation of node 1 is D1, the deformation of node 2 is D2. Okay. We also know that we have in general, so this is kind of a general case, not our equilibrium case. Okay. We have nodal forces F1 and F2 being applied on our nodes. Okay. And we're going to use the positive X convention here, where the positive, all arrows are pointing in the positive X direction. Okay. Okay. And so if we match this diagram up with our static equilibrium case, okay. Okay. What we see is that F1 is equal to minus T, right? Because in our static equilibrium case, our tension T was going to the left, right? So F1 here must be equal to minus T, and F2 is pointing in the same direction as T. So F2 is equal to T. Okay. All right, and so if we take this expression, plug in for T, okay, because we have our expression for T, we have it up here, okay? What we get are the following two equations. And I'm going to skip a step for F1. I'm just going to distribute that negative through. So we have F1 is equal to EA over L times D1 minus D2, okay? And F2 is equal to EA over L minus D1 plus D2, okay? And of course, I've rearranged the terms just to make it kind of, a little bit obvious for what the matrix set of equations that we're going to set. Okay? All right, so if we transform this into matrix form, we can see here we have F1, F2 is equal to, we have a factor of EA over L on every single term. So I'm just going to factor that out of the entire sets of equations. Okay. E over L, 1, minus 1, minus 1, 1, D1, D2. Okay. Or this thing in the middle right here, this is our element stiffness matrix for a truss. So it looks very similar to a spring. Okay? The only difference is that instead of the spring constant being out there in front, we have this factor E times A over L. So that E times A over L, you can almost think of it as kind of like an effective spring constant for a truss element. But actually, trusses and springs deform in exactly the same way. Springs can only compress and tension, have compression and tension. Okay, it's just that the numbers that you plug in are just slightly different. Okay, and so this makes things simple. And so we're going to do. I have one example here for a 1D case, but what you're going to see is that it's the exact same process, and then from there we're going to move on to 2D truss stuff. Okay. All right. Any questions on this? Okay. All right. So let's do an example here to kind of show this in action. Okay. So let's say we have a three bar assembly. Okay. And so it looks like this. A little bit ugly. Okay. Did I tell you guys my wife actually follows my YouTube channel, which sounds very sweet, but she only does it so that she can like look and find drawings that I make during my lectures and just roast me about it. It's terrible. And I married that woman. She's great. I love my wife. Okay, so we have three elements here. We have four nodes. Okay. Nodes 1, 2, 3, 4. Let me label the elements. So we have element A, element B, element C. Yeah. I'm going to use lowercase letters just so we don't get confused with the variables here. Okay, so let's list out the properties. So elements A and B have the same Young's modulus. Actually, let me do this just so it's not confusing. I'll list out each one individually. So we'll do element A. Element A has a length is equal to 30 inches. It has a Young's modulus of 30 times 10 to the 6th psi, and a cross-sectional area of 1 inch square. Okay, element B. Element B is identical to element A. So element B has a length of 30 inches, has a Young's modulus of 30 times 10 to the 6th psi, has a cross-sectional area of 1 inch square. Okay. Element C is going to be a little bit different. So element C has the same length. So element C has a length of 30 inches. The Young's modulus for element C is going to be half of that. So it's going to be 15 times 10 to the 6th psi. And it has a cross-sectional area of 4 inches square. Okay. All right. Let's look at the boundary conditions. And so nodes 1 and 2, or 1 and 4, excuse me. Node 4 is literally inside the wall. So nodes 1 and 4 are going to be fixed. So that's going to be our Dirichlet boundary conditions. And let's assume that we have a single force F being applied at node 2. Okay. So we have a force F, and its magnitude is 3,000 pounds. Okay. That's applied at node 2. All right, so we're going to use our direct stiffness method to solve the system. Okay. So we're going to go through the same method that we did in the last example before on Tuesday. So we're going to write out their element stiffness matrices. We're going to assemble. We're going to apply boundary conditions, and we're going to use MATLAB to solve. Okay. All right. Any questions on this, on just the setup for the problem here? Yeah.
Just a kind of general question. Why don't we say kilopounds?
Kilopounds. That's a good question, actually. Yeah, I'm not sure. Yeah, it's I think just the maybe because I think kilo is an SI thing, and then pounds is an English thing. But so kilopounds assumes 1,000 pounds, but I guess those two ideas never met or never became a thing. But it does make sense. Yeah.
How are the three elements connected? They're just touching each other, or
Yeah, so they're just touching each other. So in reality, if you have truss elements, technically the definition is that you have a pin support. So there's kind of like a what do you call it? Just a pin there. So technically they can rotate past each other, but for all intents and purposes, you can just assume that they're just kind of touching. Yeah. This could just be one long rod, and we've just kind of broken it up into three sections. Yeah. Yeah, there's no kilo inches or decimiles. Yeah, it would be useful. SI makes so much sense, but half of our in America, a lot of our world is in English units, so we got to learn it. Okay, all right. So let's go ahead and start solving. All right. What you'll find out about these problems is that they're not, once you kind of get used to the methods, that they're not difficult. It's just annoyingly kind of long. It's just a lot of writing. All right, so let's start with the element stiffness matrices. Okay. So let's start with elements A and B. And for the truss bars, because we have this factor of AE over L in front, usually what I like to do is I like to kind of compute this off the bat, just so we don't have too many variables kind of floating around. And so if we look at element A, we have a Young's modulus of 30 times 10 to the 6 psi. We have an area of 1 inch square and a length of 30 inches. Okay. Luckily, all of these things are in the same set of units, so we have no feet or anything like that. So we can just straight up multiply this. Okay. And so we take 30 times 10 to the 6, multiplied by 1, divide by 30, we get 10 to the 6 pound per inch. Okay. And so for element stiffness matrix for element A, so we have Ka is equal to 10 to the 6, 1 minus 1 minus 1, 1. Okay. Don't forget the nodes, and so you need to indicate which nodes that this element is connected to. So we have a D1 and a D2. Okay. All right. Next, we have element B. Luckily, element B has identical properties as element A. So we perform this multiplication, we get 10 to the 6 pound per inch. Okay. And so KB is going to be 10 to the 6 times 1 minus 1 minus 1, 1. Right. What is going to be different about element B is that it's connected to nodes 2 and 3. So it's going to be D2, D3. Okay. Then we have element C. So element C, let's compute its effective spring constant. So we have AE over L. Okay. We multiply all of those things out. We get 2 times 10 to the 6 pound per inch. Okay. And so if we have the element stiffness matrix, that's 2 times 10 to the 6, 1 minus 1 minus 1, 1, D3, D4. Okay. Okay. All right, so not too bad here. Just a lot of writing to do. Okay. Next step is going to be assembly. So let's assemble all of this into the same linear system. And so we have 4 nodes here. We have 4 nodes and we have a 1D problem. And so that means our system is going to be 4 by 4. Let's go ahead and write it out. And so we're going to have F1, F2, F3, F4 equal 2. Okay. So we have a 4 by 4 matrix. So that's 4 rows and 4 columns. So D1, D2, D3, D4. Okay. Labeling the columns is optional, but I like to do it just because it helps. It just helps me. Okay. All right, and so we're gonna insert our element stiffness matrices into the right pieces. Okay. Right. But before we do that, I'm gonna do something here just to kind of save you a little bit of work. Okay. So this is it's not really a trick, but it's just a way to kind of save yourself on a ton of writing, right? If you look at our element stiffness matrices above here, all of them have this factor of 10 to the 6th out in front. Okay. We could easily kind of write these in, and so we can start writing 10 to the 6th, minus 10 to the 6th, minus 10 to the 6th, 10 to the 6th, right? So we could easily do that, and that's actually technically the correct way to do it. Okay. But remember, we're working with linear systems here. And so with linear systems, anytime you have a number that's multiplied through the whole thing, you can just kind of pull it out. And so what I have here is I have an arrow that's kind of pointing to the front of the linear system. Okay. And what I'm going to say is that, we're going to factor out a 10 to the 6th from this entire thing. Okay. So now that 10 to the 6th come out in front, and then everything in the middle here, or inside the matrix it's kind of implied that we're going to multiply 10 to the 6th by it. So it's just something to save yourself on some writing. It'll help you a lot on the homework for sure. Because these problems are very tedious already. And so anything that you can do to save yourself some writing or some tedium kind of helps a lot. Okay, so let's go ahead and start inserting our element stiffness matrices. And so, in this case, we have three elements all in a row. And so lining them up is actually pretty easy. So we have element A. Okay. Element A is connected to nodes 1 and 2. Okay. So that's going to be the first 2 columns and the first 2 rows. Okay. Next, we have element B. Element B is connected to nodes 2 and 3. And so if we draw that out, that's going to be the second row, third row, second column, third column. Something like that. Right, and then we have element C. Element C is nodes 3 and 4. Okay, so that's the last 2 rows and the last 2 columns. Just like that. Okay. All those squares should be the same size, but now that I think about my wife making fun of me now, I'm conscious about it now. Okay, so let's fill in the numbers here. And remember, whenever we have any overlapping entries there, we're just going to add those together. Okay. And remember, we have the 10 to the 6th out in front, so that saves us a bit of time. So we have 1, minus 1, minus 1. Okay. We have a positive 1 that comes from element A in the bottom left, plus a positive 1 that comes from the top left, or bottom right and top left of element B. So that's going to be 1 plus 1, which is going to be 2. Okay. Then we have minus 1, minus 1. We have a 1 in the bottom right coming from element B, plus a 2 coming from the top left of element C. So that's going to be a positive 3. Okay. Minus 2, minus 2, and 2. Okay. And of course, everything else is zeros. All right, and so that's the assembly step. And so, pretty straightforward in this case. We just have, 3 squares kind of lined up together. But of course, you saw from the example last time, it can get a bit more complicated than that. Okay. Any questions on this part here? Okay. All right, so last step is we're going, or second to last step is we're going to apply boundary conditions. All right, so we have 3 boundary conditions to apply here. So we have a Dirichlet boundary condition on nodes 1 and 4. Okay. So let's go ahead and apply that first. And so remember, for a Dirichlet boundary condition, we're going to replace that entire row. Okay. So this first row in the matrix is going to become 1, 0, 0, 0. I'm just erasing all of it just so I can put it in a different color. Okay. And then we're going to put a 0 here in the forcing vector as well. Okay. And then for the last row, we're going to do the same thing. So we're going to place this entire row by 0s and 1s. Okay. But since we're on the last row, we're going to put the 1 on the last column. Okay. Remember, the 1 for a Dirichlet boundary condition, the 1 goes on the main diagonal. Okay. And then the other boundary condition that we had was our Neumann boundary condition on node 2. This was a force. The amount of force that we're applying there is 3,000 pounds. Let's go ahead and replace that. Use purple. Okay. We're going to put 3,000 pounds on node 2. Okay, so that's going to replace the F2. And since there's a Neumann boundary condition, we don't make any changes to the matrix. We only change the vector. Okay. And the F3, we don't have any force being applied there. We don't have any Dirichlet boundary conditions, so we're just going to put a 0 into that. Okay. All right, and so now our system is ready to solve, and so we can plug this guy into MATLAB. I'll let you guys kind of verify that just kind of for the interest of time. But if you plug this entire guy into MATLAB, or your graphing calculator, or the website, or however you choose to solve this system, we obtain the following results. We get D1 is equal to 0 inches. We get D2 is equal to 0.0018 inches. You have D3 is equal to 0.0006 inches. And D4, since it's fixed to the wall, is 0 inches. Right. All right, question from the chat. Can you explain again why we replaced F3 with 0? Sure, of course. So F3 here is 0. And so we go back to the diagram here, and we look at node 3. So node 3 doesn't have any, there's no Dirichlet boundary condition on it. So there's no fixed support, and there's no forces being applied on it as well. And so in those cases, when you have a node that doesn't have any, basically it has no boundary conditions applied to it, we default by just replacing that forcing to zero there. Yeah. You can almost think of it like it does have a Neumann boundary condition, but it has a Neumann boundary condition of zero, like zero force. Yeah. Mm-hmm. All right. Any other questions on this example here? Okay. All right. So we have about 24 minutes left in class, and so I want to start the 2D stuff. I think what I'll do is I'll probably push the homework assignments back because we're not going to finish the 2D stuff today. I'll probably push that due date back by about half a week. So just to give you guys some more time for that. Okay. But let's start this concept here. So let's talk about direct stiffness problems in 2D. Or I guess more specifically, truss and spring problems in 2D. All right, so we're jumping up a dimension. Okay. All right, so far, all the problems that we've considered have just considered one-dimensional deformation, right? So we just have a simple elongation or simple compression of a spring or truss element. Okay. This is fine, but in reality, you're going to have situations where you need to consider multiple dimensions of deformation. Okay. In particular, for trusses and springs, this occurs whenever you have a structure, whenever you have an assembly where the elements are not parallel to each other. And this goes for 3D as well. Okay. So, for example, one geometry that you're going to see in your homework looks like the following. Okay. This is probably the longest problem on the homework, but I do want to show it to you. Let me just draw straight lines. None of this cylinder nonsense. Okay. It's either like that or it's upside down. Okay, and so each of these bars here, so we call this truss element A, truss element B, C, D, and E, okay? Right. Here we have a situation where we have a truss structure, but the truss elements are not parallel to each other. And that gives rise to a two-dimensional geometry, okay? And so, when you're looking at two dimensions, okay, we're no longer going to be considering just one component of deformation at the nodes, right? Because if you look at the deformation of this node here that I highlighted in purple, right? We need to consider its deformation in two dimensions. So we need to consider its deformation in the x direction as well as the y direction, right? And so that just kind of comes with the territory of increasing dimensions, right? Deformation in reality is a vector quantity. That means it's going to have components in multiple dimensions. Okay. We've been treating it like a scalar just because we've only been looking at 1D geometries. But when you get up to 2 dimensions and 3 dimensions, you need to solve for all components of the deformation. Okay. And so that means our methods are going to have to be improved, or they're going to have to be modified to account for solving for multiple deformation modes. And so that's the purpose. That's the purpose of this section here. Okay. So basically, taking our methods for direct stiffness and seeing how they kind of translate to two dimensions. Okay. Okay. The primary difficulty that we're going to face is that when we're forming our element stiffness matrices, when you have elements that are not parallel to each other, the element stiffness matrices are not going to match up. Okay. And the reason for that is that the derivations that we've done for the element stiffness matrices, we've always assumed that our truss or our spring is always parallel to the x-axis. Okay? And so when our truss or our spring is deforming, it's deforming in the principal x direction. Okay. So that's why, in one dimension, we only have to compute one component of deformation, okay, one per node, because it's assumed that, that's the only way that it can be. And two dimensions, it gets a bit more complicated. So, because traditionally, just for the sake of simplicity, we like to draw our x and y coordinates in kind of its standard form. Okay. Okay. And so standard Cartesian coordinates usually has the y-axis going vertically upwards, okay, and has the x-axis going horizontally, just like that. Okay. But in reality, if we have a two-dimensional structure with trusses and springs, we're gonna have elements that don't conform to this, and so they're gonna point up in a diagonal direction. Okay. And so just look at the structure that we have up there, right? We have elements going in kind of this direction, right? Right, not in the standard X and Y. Okay. This is an issue, right? Because the element stiffness matrices for these elements assume that the standard X direction is aligned with the element. Okay. And so the kind of the upside to this is that we can't, when we get to the assembly step, if we just use the element stiffness matrices as we have them right now, we can't combine them because they're all kind of been defined under a different set of coordinate systems. In order to combine them, we have to kind of, and the term that we use is transform. Okay. And so we have to transform these element stiffness matrices into one kind of unified coordinate system. And so the first part of this 2D section here is going to be a transformation of variables. And so we're going to learn how to do change of variables between different coordinate system, change of coordinates, okay? And then we're going to apply that to our element stiffness matrices. Okay. All right. So that's kind of the motivation for kind of why we're about to go through this. And so it's going to be a lot of trigonometry, a lot of linear algebra, but you know, we'll get to the end. Any questions on this so far? Okay. All right. So the next topic that we're going to go over is it'll probably bleed over until next week, but let's go ahead and start it. And so it's going to be transformation matrices. And change of coordinates. Okay. All right. So let me start by saying that, you know, a coordinate system is nothing more than just a way to describe a position or a way to describe a vector. Okay? Okay. You can almost think of them as just like looking at the same object from a different perspective. Okay. Okay. So let me give you an example. So I'm standing here at the front of the classroom, and I can look at the overhead projector, right? From this perspective, you know, it looks to me like it has a certain width, has a certain height, and a certain depth, you know, within going into, you know, towards the end of the classroom. But if you guys were to look up from your seat and look at the projector, right? It's the same projector, it's the same object, but the dimensions and the way that you describe it will be different because your perspective is different, right? Just because you're looking at it from a different location. Coordinate systems are kind of the same way. So coordinate systems are just different ways to describe the same vector in this case. Okay. So let me visualize it for you. So let's say that we have a certain vector. Okay. So I'll call it U. And I'm going to draw that exact same vector over here. So another test of my artistic ability. So let's see if I can copy. I know the arrow looks different, but the size and the direction should be exactly the same. Okay. Okay. So here I have identical vectors, right? Okay. This is going to be a little bit weird because, you know, visually we can see the vectors, right? But if we were to describe these vectors mathematically, you know, usually we would express this vector in terms of its components, right? And so we have u, x, and u, y, right? Where, you know, if I were to draw kind of the standard x and y coordinate systems, okay, so we have x and y like this, right? Ux would be the component of this vector in the x direction, okay? So ux would be this distance right here, okay? And then uy will be this distance right here. So if we were to describe this mathematically, we would say that u vector is equal to ux comma uy, okay? That would be kind of the standard way to describe a vector. That's kind of how we've learned it in most of our classes, right? What if I take that same vector, but I rotate the coordinate system a little bit, right? So instead of being x with y vertically up and x horizontal, let's describe it like this. And so let's draw the y-axis like that and the x-axis like that. Okay. So we'll call this x prime, or excuse me, x hat and y hat. Okay. And the way that we've obtained this is we've rotated by an angle of theta. Okay. We can describe the same vector, and so if we were to, do the same exercise, okay, and we were to write out the components of this vector, not with respect to the original coordinate system, but this time with respect to our rotated coordinate system, okay, we'd have ux prime or ux hat and uy hat. Okay? And so we would say that u vector is equal to ux hat, comma, uy hat. Okay. So the way that we describe the vector is different depending on what coordinate system, depending on the coordinate system that we're using. But it's the same vector, it's the exact same vector, right? And so what we can say is that we can say that these two expressions here are equal to each other, right? Because it's the same vector. Mathematically, we can do this, but we're going to use the unit vectors. And so, typically we express, or at least the way I learned it, I express components using a parentheses notation. But if you were to use the unit vectors, it would be something like this. We have ux times I hat plus uy times j hat is equal to, excuse me, sorry. I'm happy right now. Okay. This would be ux times I and uy times j. Okay. I'll put a vector sign on top to indicate that they're vectors. Okay. And on the right-hand side, we have ux hat. That's going to be multiplied by the unit vector in the x hat direction. So this would be I hat plus uy hat j hat. Okay. The i's and j's are unit vectors in their respective coordinate directions. All right, so these two expressions should be equal to each other because it's, they're both describing the exact same vector. Okay. All right. And so our next step here is, we're going to kind of work on this expression a little bit, and we're going to plug in for the unit vectors, to make it a little bit easier to kind of parse mathematically. So what we have here is an equivalent statement. It's just not really useful to us, just because we can't really draw any information. So let's substitute. Because right now, this expression here is a little bit hard to parse because, the exact relationship between, I vector and I hat vector, right? So those are unit vectors in the original coordinate system and rotated coordinate system. That's not 100% clear, okay? So we want to substitute in. And in particular, what we're going to substitute in for is these ones right here, okay? Okay, you'll see what I mean in just a second. So, okay. And so to do this, we're going to use geometry and trigonometry. Okay. So a little bit of a throwback. So let's draw the I vector. Okay. So I vector is a unit vector in the traditional x direction. So it's a horizontal vector like this. Okay. But it's a unit vector. And so a unit vector has a length of 1. So the length of this vector here is 1. Okay. Let's also draw the components of this I vector in terms of the rotated coordinate system or the hat coordinate system. Okay. And so we know that our rotated coordinates, we took our traditional coordinates and rotated it counterclockwise by an angle of theta. Okay. And so we're going to have one component like this. This angle here is theta. Okay. And right, and so we're going to form a triangle like this, where this leg of the triangle right here, I'm going to color it in purple. Okay. We'll call this A vector. Okay. So A vector is unique because it's going in the x hat direction. Okay. And then we also have this vector, which I'll call the B vector. Okay. Notice how they're perpendicular to each other. A vector and B vector are perpendicular. Okay. But B vector is a vector in the y hat direction. Okay. All right. So we've drawn ourselves a triangle here, a right triangle to be more precise. Okay. So what we're going to do on Tuesday is we're going to look at this just trigonometrically, and we're going to use the angle that's given to us. We're going to use sines, cosines, and we're going to use the fact that the hypotenuse of this triangle has length 1, and we're going to form a relationship between the unit vectors in both systems. All right, any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for today, and so we'll pick this up again on Tuesday. Remember, homework problem set 1 is out there, so definitely get started on it. You can do the first half on the 1D problems, and then next week we'll learn how to do the 2D problems. Okay. I'm probably going to push the due date back for problem set 1 because we're probably going to spend most of next week doing 2D problems. So just expect it to be pushed back by about maybe like half a week. Okay. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend, and I will see you guys next week. Thanks, guys. Yeah, I mean, I can probably, yeah, you just have to find it. See you guys. Have a good weekend. See you, Dominic. See you guys. Have a good weekend.
It's the distance. All the five, it's a 5 by 2.
You too. See you guys. Good night.